A functioning society needs to be structured in such a way that it maintains as a high standard of living as possible for everyone. This includes that society is egalitarian to prevent conflicts, that we do not consume resources faster than either the earth or the society can recreate them, and that we use science and technology to resolve problems and make people's lives easier. This is what the Zeitgeist movement means with a resource-based economy. One of the first questions that comes up with this framework in mind are, is there enough resources to be able to live in a modern global society? So, let's try to answer that. Is there enough for everyone? The resources I intend to discuss are those that satisfy our most basic needs and thus lay the foundation for our ability to satisfy our higher social needs. I will talk about food, water, energy and materials. As a point of reference, I will wherever possible base the conclusions on the average Swede, since this was originally a Swedish lecture, and the average Swede works very nicely as a benchmark that most people would qualify as a person with a high standard of living. I will also use existing commercial technologies and then extrapolate how many people the Earth can support. The average Swede consumes 822,000 dietary calories of food per year, uses 344,000 liters of water, and consumes 69 megawatt hours of energy. However, it's important to point out that we're currently using resources extremely wastefully, and new efficient technology is developing very quickly. So keep in mind that these extrapolations are very conservative when it comes to the carrying capacity of a resource-based economy if it were to be implemented. Food. We currently produce 7 quadrillion dietary calories per year, which means that we should be able to satisfy 8.6 billion people, or roughly 1.3 kilograms of food per person per day. However, this is far from our current potential. Vertical farming is the method where you grow food, you guessed it, vertically, in different ways, usually in shelves, and this can be combined with other types of agriculture methods such as hydroponics, which entails cultivating in water instead of soil, aeroponics, cultivating in air, and aquaponics, which are forms of circular systems using fish to enrich nutritional content in the water for the plants. All these different systems are already being used commercially in the world at places such as, for example, Chicago and Singapore. Since these facilities can produce 10 times as much food per square meter and uses almost no water, energy, land, pesticides or fertilizers compared to traditional farming, there is virtually no limit how many people we can feed. Meat production is extremely costly from an energy perspective and affect the environment very negative compared to the cultivation of plants. We should, as far as it's possible, try to avoid meat in our diet, but it's still completely possible to provide protein-rich meat to the entire world population by breeding fish through aquaculture. Worth mentioning in this context is in vitro meat, cultured meat, which has the potential to replace animal breeding for meat production altogether, in which case this would significantly reduce the need for energy, land and water. Out of those 344,000 liters of water that the average Swede currently uses, only 108,000 liters, perhaps less, is necessary in a resource-based economy, because water consumption could be reduced by 69% by utilizing hydroponics, aeroponics and similar modern agriculture methods. This would mean that with the water reserves we have today, 55.2 trillion cubic meters, we can provide 511 billion people with clean water. If we then assume that just 7.3% of our water needs to be recovered each year, we would need 27,070 desalination plants, which is just 60% more than the number of facilities in operation today. Note that this is for a population of 511 billion. With today's population, we would need a measly 378 desalination plants. And all this is based solely on the renewable freshwater resources already available in our current global water system. We thus potentially have access to much more water through desalination and purification. Energy. With this strategic efficiency train of thought in regards to water and food, it wouldn't come as a surprise if the energy need also decreased drastically as a direct effect of this without compromising the standard of living for our average Joe. But let for the sake of argument still assume that we need to be able to produce 69 megawatt hours per person. The energy sources I'm going to cover is geothermal, wind, solar and hydropower, as they are renewable and do not generate hazardous byproducts, such as for example carbon dioxide and nitrogen oxides. Geothermal power. This is the energy originating from the Earth's interior by radioactive decay. A study conducted in 2006 at MIT showed that it's possible to extract 11.11 million terawatt hours from continental US alone. If we are allowed to extrapolate this number to the entire globe, this means that we could produce 588.5 million terawatt hours. For a population of 10 billion, this would last 1,900 years, assuming no renewal, which does in fact occur through radioactive decay. Geothermal power plants can theoretically be placed anywhere on Earth, but it's advantageous to place them near the lines where tectonic plates meet. Iceland, for example, almost exclusively use geothermal power. Wind power. The effect available from wind is roughly 428 terawatts, or enough to supply 54 billion people with power. This would, however, cover 7.95% of the Earth's land area, but even if this is not desirable, we have the possibility of placing wind turbines offshore. Only the capacity of coastal wind power could provide energy for about 21.1 billion people. Solar power. The energy from the sun that reaches the Earth is 1,360 watts per square meter. This means that if we were to harvest all the energy that strikes the Earth, 174,000 terawatt, we would have the energy for 22,300 billion people. It becomes strikingly clear that if we could only capture a fraction of that energy, we could meet the demands of many billion from this source alone. The world's largest solar power plant produces 392 megawatts, and with 200,000 of these plants placed over the world, we would be able to supply a population of 10 billion. It should be pointed out that the collectors used are heliostats, mirrors to direct sunlight to the generator in the center of the field, and thus uses minimal amounts of rare earth metals. If this were done, it would take up 20% of all deserts on Earth, excluding the polar deserts. Hydropower. Energy from water comes in a wide variety of sources, such as wave, tidal, ocean currents, ocean thermal, potential differences, and osmosis. I will not go through them individually, but with established commercial technology we could produce 10.4 terawatts, enough for 1.32 billion power-thirsting average Swedes. However, our ability to extract energy from the ocean is only in its youth. New technologies that have the potential to provide 10 billion people with power have been developed. Examples of this are technologies that extract energy directly from the Gulf Stream or from very slow-flowing rivers. So far I've just taken up large-scale energy production, but the fact is that using, for example, piezoelectricity, the extraction of energy from pressure, or new nanomaterials based on graphene, we can produce all the energy that we need when we need it directly from our infrastructure. So we hardly need any power plants at all. Materials. When it comes to materials and other natural resources, we have already seen that a more holistic train of thought can lead to huge savings on our resources, without affecting our standard of living negatively. Through vertical farming, we can use up to 40% less of the Earth's ice-free surface. And what's important in this context is that we use resources as economically, in the true meaning of the word, and efficiently as it's technically possible. It's important that we have a sustainable system theory approach focused on maintaining an access abundance rather than a material abundance. In fact, almost no resources leave the planet, so the key here is to structure society and industry synergistically with renewability in focus. That was all. Thank you for listening.